Hello and welcome to this course. This course is entitled as Introductory Course on Design of Interior Permanent Magnet Motor, IPM motor. First of all, let's have a look on the course content. In this course, our objective is design of a 4 kilowatt motor that its rated speed is 1800 RPM. The voltage of DC link is 72 volts. We assume that the motor will be fed using a battery pack, and the voltage of battery pack is 72 volts. The desired efficiency of motor is 95%, and the desired power factor is 0.9. In this example, we also have two mechanical constraints. One mechanical constraint on outer diameter of stator lamination, and another constraint is on motor stack length. The outer diameter of stator lamination should be within 15 centimeters, and the stack length should be lower than or equal 26 centimeters. So at the first, we talk about the calculation of base speed, motor base speed, and selection of the number of poles and the number of stator slots. Actually, the selection of the combination of a slot pole combination, number of stator slots, and number of poles. So this combination is important because it determines the weight of motor, and the performance of motor is highly affected by this combination. After talking about these three main parameters, base speed, the number of poles, and the number of stator slots, we will start the preliminary design of motor, analytic design of motor. We talk about classification of variables and then design workflow. In this course, we will use three software: the ANSYS Maxwell software for finite element calculations, finite element analysis of motor, and the Excel software for analytic design, and MATLAB software for derivation of some motor characteristics. Sometimes during the course we need to write some shortcodes to drive some curves and some properties of motor. These are the equations that I will explain this equation, and we will implement these equations into the Excel file for analytic design of motor. Here we will talk about the magnet sizing, how to determine the proper size for magnets. This is an example. After analytic design, we will start the finite element analysis of motor. So we need to do different kinds of simulations, analysis for calculation of properties and characteristics of motor. First, as you can see here in this slide, the motor sketch, the rotor type is a V-type motor, V-type IPM motor, and this picture shows the motor sketch. First, I will explain how to create a fully parametric geometry and fully parametric design in the software, and talk about the boundary conditions, applying boundary conditions, and definition of material for our case. Okay, setting of the material, and then definition of magnets, and definition of magnetization direction for each magnet, and then calculation of magnetic loading. The magnetic loading is the first analysis that we will do by finite element method. Magnetic loading calculation is our first analysis. This is flux distribution in the middle of air gap, and this is the value of magnetic loading. Then we calculate the field that is generated by armature field, that is generated by currents in a stator winding only. Okay, in this analysis we will remove magnets and we only excite the stator windings, 3 phases. So before that we define the stator winding. I will explain how we should define the stator winding, and then we will calculate the flux distribution to a stator winding. This is a magnetic field in the middle of air gap that is generated by a stator winding. The next analysis is demagnetization study. As you know, we need to do demagnetization study to verify that the magnet operation, to verify that in the steady state operation of motor, we don't have the risk of demagnetization of magnets. So we need to consider the worst case. Okay, we need to consider the worst case condition and calculate the magnetic field in magnets in the worst case, and confirm that even in this condition we are before the knee point. Okay, here we are in this region, and then I will explain how we can calculate the static torque of motor. As you know, the static torque is one of the most important characteristics of each of electric motor. This curve is static torque versus the stator phasor current angle, alpha is. And as you know, in IPM motor, we have 2 kinds of torque, the electromagnetic torque and the reluctance torque. And because of this, the static torque curve looks like this curve. The next analysis is calculation of back EMFs, motor back EMFs. In this simulation, we will do a transient simulation with a fixed speed for rotor. In this simulation, a rotor is rotated by a fixed speed, and then we calculate the voltage induced in 3 phases. In this step, we also calculate the cogging torque, the motor cogging torque, and then I will explain how we can calculate the dq quantities in the rotor reference frame and stator reference frame. For example, this figure shows the D and Q flux in a stator reference frame and then in rotor reference frame. For this curve, as you can see here, the Q flux in rotor reference frame is 0 because this is back EMF simulation and we don't have any currents in stator winding, so the Q flux is 0. I will explain these calculations, and I will explain the results. Finally, we will do the steady state simulation. This is a transient current fed simulation, and in this analysis we excite the stator winding by its rated current at a proper angle, at a proper alpha IE, and then we calculate the steady state torque and torque ripple of motor. So our motor should be capable to generate the average torque equal to the desired value for its steady state operation. These are flux linkages, and this is the Q flux in rotor in a stator reference frame and then in rotor reference frame. And then we investigate the SQ study for reduction of cogging torque in motor by selection of a proper angle for skewing of a stator core. And we will compare the results of non-skewed model and skewed model, and we will investigate how skewing can reduce the cogging torque. This, for example, compare this result. This model is without skewing, and as you can see here, the torque ripple is around 10%. This is a steady state torque for a skewed model, and the torque ripple is below 2%. Then we will calculate the saliency ratio of motor. The saliency ratio is defined as the quadrature inductance divided by direct inductance. So first we calculate quadrature inductance and direct inductance, and then we calculate the saliency ratio. This is the equation for calculation of electric torque. The first part is reluctance torque, and the second part is the electromagnetic torque. And in IPM motor, both kinds of torque exist, and also for control purposes we need to know the value of LQ and LD. So I will explain how we can calculate the LD and LQ using finite element software. This is saliency ratio for this example, and this is the average torque that is calculated by this equation. And then I will talk about the calculation of torque speed curve and another curves. For example, the terminal voltage versus speed. Okay, for this we will write a MATLAB code, and I will explain how we can derive the torque speed curve for our design. And okay, this is the calculation. This is the constraint, and these are the calculations that we need to do for derivation of torque speed curve. And I will explain also the calculation of iron losses and other parameters of motor, like as power factor and so on. Let me to show you the Excel file. I developed this Excel file for analytic design of motor, and we will use this Excel software for design of motor. This sheet is for rating, motor rating, and this is main dimension sheet. The analytic design is analytic design of motor is doing in this sheet, and I implemented the analytic equations in this sheet, and these are design parameters. Okay, and this sheet is for sensitivity analysis. For example, this sensitivity analysis is the DO, the outer diameter of stator lamination, versus the aspect ratio. I run this analysis, for example. And this sheet is for selection of the slot pole combination. Okay, and then we have two sheets that are AWG and SWG table, and some data and tables related to the material properties, for such as the mass density of copper, mass density of stator lamination and magnets, and resistivity of copper, that we want to use copper for stator winding. Okay, and these are the files that we will generate from zero again during this project, and this analysis that I explained. We need to do these steps. We need to create these designs for derivation of motor characteristics using finite element method. First, we create the fully parametric design. These are design variables. Some of them are dimensions, and some of them are motor characteristics, like as the phase, current, resistance of phase, number of turn per coil, okay, and so on. This is magnetic loading analysis. This is the flux waveform in the middle of air gap. In this analysis, the currents in stator winding is zero, and this field is generated by magnets only. We calculate the armature field. This is the magnetic field that is generated by armature field only. And this is the flux waveform, flux distribution in the middle of air gap. As you can see here in this design, in this analysis, I removed the magnets. Then we will do the demagnetization study, considering the worst case. And then we will calculate the static torque, the motor static torque. Here, as you can see this curve, the static torque versus stator current phasor angle, alpha is. And then we will calculate the motor back EMFs, back EMF simulation. These are phase back EMFs, linkage flux, dq flux in stator reference frame, and dq flux in rotor reference frame. And finally, we will do the steady state analysis for calculation of steady state torque. This is a steady state torque, as you can see here. In this example, the red curve is the torque that is calculated by finite element method using ANSYS Maxwell software, and the green curve is our calculation of steady state torque using this equation. So as you can see here, the results are close to each other, and it shows that our procedure is correct. And this is saliency ratio. This is, for example, the iron losses. We need to calculate the iron losses for calculation of motor efficiency, and this This curve shows the LQ and LD. Okay, we will cover these contents during this course. And let's start the course from the next video.